Okay, thank you everyone for coming. It's my pleasure to introduce our own Daniel Nakano. He's going to talk today about a tribute to the work of Cline, Parshall, and Scott.
Okay. So thank you, Scott, for the introduction. I'd like to thank the people for participating in this tribute today. I know that some people were there in Atlanta, and so I thank you even more if you've come a second time to this tribute. So, all right. So I'm going to start off with, whoops. Let's see. Hang on, maybe I have to just.
If you click on the slides, you should be able to scroll.
Oh, there we go. Okay, so now we can raise our hands. So how many people actually owned a device like this? Also, how many people actually know what this device is? I don't see any hands raised. Oh, good. I see lots of hands raised now. All right, good. All right, so this is a television set, of course. It's from like the last century. And as you know, television shows were a hallmark of the latter part of the 20th century. And during this time, the CPS collaboration, starring Edward Cline, Parshall, and Leonard Scott, they were like a hit TV show in mathematics, and their run lasted for about 3 decades. And when I was an early career mathematician, I sort of eagerly watched old episodes of CPS. I looked at their old papers, and I eagerly awaited the new episodes, and those usually involved ballistic conjecture. Okay, and when they would actually come on the archive, and I would actually look at them almost immediately after they came on the archive. Needless to say, their work played an essential role in the development of algebraic groups. So in this talk, I'm going to touch on some of Cline-Parshall and Scott's work. I won't be able to go over the entirety of their work, but I'm going to touch on some of the most important work that they did. And so I'm going to focus first on the cohomology of finite groups of Lie type. And then I'm going to talk about rational and generic cohomology, and this features guest star Wilbert van der Kellen. And then finally, I'll talk about highest weight categories. These are sort of equivalent to looking at quasi-hereditary algebras. And if you were at Jack's PhD thesis defense, this idea came up prominently in his work. So, all right, so let me start off with the general setup. So K is going to be an algebraically closed field, characteristic P bigger than 0. And one of our favorite players is the simply connected algebraic group. Sometimes I'm going to think about it as a group scheme over the field FP. Okay. So if you want to think about SLN, you can think about SLN, or if you want to think about E8, you can think about E8. So F is a Frobenius map. It's going to go from G to G. And this is a very important map because we're able to construct 2 objects with the Frobenius map. The first map is the Frobenius kernel. So you take the scheme theoretic kernel after you iterate the Frobenius R times. And then you could actually look at the rth iteration of the Frobenius and look at the fixed points on G. And that gives you GFQ. Okay, and this is going to be a finite Chevrolet group. So, you know, you can just sort of think of SLN FQ, where the matrix entries are in FQ. Now, with this setup, there are 3 major objects. There are representations for the algebraic group, the representations for the Frobenius kernel. So the way you should think about the Frobenius kernel is these are sort of representations for the Lie algebra in some sense. And then you have representations for the finite group. And so you can restrict representations down from the algebraic group down to either the Frobenius kernel or down to the finite group. And back in the 1960s, people were very much interested in studying simple modules between these categories. And Curtis showed that if you take a module for the Lie algebra with restricted weight, then you can actually lift it to the algebraic group. And then when you restrict it down to the finite group, it turns out to be simple also. And so you can actually get a bijection between irreducible representations for the Lie algebra and representations for GFP this way, okay, just by using this triangle. And then Steinberg, with this famous tensor product theorem, allowed us to actually figure out what the rational representations are for G by just looking at representations for the Lie algebra, restricted ones. Later on, Ballard and Janssen studied projective modules for this algebra. So this GR is actually, the module category is equivalent to modules for a certain finite dimensional Hopf algebra. So you can look at projective modules, and you can ask whether their structure lifts to G or not. And so Ballard and Janssen showed that they do as long as the prime is big enough. And later on, it was conjectured that these projective modules always lift for all P. And Donkin formulated a conjecture involving tilting modules in his 1990 MSRI lecture, where he said that certain tilting modules would actually restrict the projective indecomposables. And so with work of myself, Cornelius, Chris, and Paul, we actually studied this conjecture quite a bit. Okay. So let's talk about Cline-Parshall and Scott's work. So their idea was to use the restriction map in cohomology. So they looked at the map going from restricting extensions for G to restricting extensions for GFQ, and they wanted to study the relationship between finite group extensions and algebraic group extensions. And they were really the first ones to discover that there's a special connection by looking at these two objects. So this paper in the publications of the IAHS, this was actually one of their first papers. Now, in one of the first results that they had in this area was to actually determine what the one cohomology is for a simple module with minimal non-zero dominant weight. Okay, so for the minuscule weights, for example, they were actually able to just figure out what the one cohomology was. And surprisingly, I mean, they didn't know this at the time, but it would actually have connections with Andrew Weil's work on Fermat's last theorem. So this work in the publications of the IAHS is actually quoted in Weil's proof of Fermat's last theorem. Okay, so they actually needed these he had actually needed these calculations for his proof.
Dan, aren't the the minimal non-zero dominant weights exactly the minuscule fundamental weights?
No, I mean, you could have, I mean, it turns out that you can actually have other ones which are not. So
I guess it depends what you mean by minimal, but maybe it's a bit of a
right. Yeah, with respect to the order. So okay, so
anyway, okay.
Yeah. All right, so the next topic I wanted to cover. So they were studying just the restriction map, and then they made this really impressive discovery. And this was the rational and generic cohomology result. This is a paper that was published in Invenciones in 1977. So basically, it says the following. So let's say I fix an I, right? So if I let the field get fairly large, so make FQ pretty big, And if I twist by the action of the Frobenius, so I can twist modules by the Frobenius by just sort of composing the representation with the Frobenius map a certain number of times. And once I do that for large enough E and large enough Q, then it turns out the restriction map's an isomorphism. So at that time, it was a very, very kind of surprising and impressive result that's been used in several applications. Now, when I was actually working with Brian, he told me a story about this theorem. He said that they proved this, I believe, on a weekend. Maybe it was like the 4th of July weekend, and so they used to stay up all night working. And he said that what they would do was they would take shifts. So 2 of them would work at a time. And so he said, well, this is why you have a 3-author collaboration. So they're able to efficiently work by just working 2 at a time, stay up all night, finish the paper off, and then get rest later on. So. All right, so another interesting thing about this paper that you may notice in the references is the following. So they reference some very famous people. They reference Saunders MacLean, and they reference Robert Steinberg. But in between these 2 references is H. Satzfiedler, aka Horace Satzfiedler. Brian told me his first name was Horace. Now, to this date, the Lécon sur la suite spectropolonginière has not really appeared in print. So I'll let you figure out, like, or if anyone can find that reference, I'd be very happy. So. Okay, so let's move on. So I'd like to talk next about CPS, the next generation. So CPS actually inspired lots of work after their work. And as with many popular TV shows, there are sequels. And many of us were influenced and have actively used the work of CPS. And I consider us part of CPS's next generation. So what I'd like to do next is show how some of the new ideas that we came up with fit into the framework of CPS's results on like cohomology of finite groups of Lie type and also rational and generic cohomology. All right. So the restriction functor is adjoint to induction. And so what kind of surprised us was people didn't really look at the induction functor very carefully in this approach. So here's something very naive to do. So you take the finite group and then you induce it up to the algebraic group. Okay, so you're going to get some huge infinite dimensional representation this way. The good thing about this functor is the quotient is affine, so the functor is actually exact. So you have this short exact sequence, so you could just take the trivial module, and it's just going to inject into this module here, this induced module, just by like using Frobenius reciprocity, and it's going to have some co-kernel like this. And now you just take a rational G module, and you could just tensor this short exact sequence on both sides. And that's what I do here. And then what you do is you actually just take the long exact sequence in cohomology. So let's do that. So here's what you get. And it turns out that when you actually take the induced module, that's going to be the same as that map from K into the induced module really is the restriction map in some sense. It induces the restriction map in cohomology. So that's what happens over here. Okay. And then you have the stuff involving the co-kernel over on this part. Now, this looks kind of innocuous, But what have we really done? Well, we actually have encoded the restriction map in a long exact sequence. And moreover, the first column sort of represents the algebraic group cohomology. The second column represents the finite group cohomology. And then the third column is kind of a mystery right now. But if you have some control over the third column here, then you could actually say something about the restriction map. And it turns out that you do have some control. And this involves the flag variety and the cohomology for the Lie algebra. So this is the algebraic group cohomology, this is the finite group cohomology, and this part involves the Frobenius kernel cohomology and the sheaf cohomology for G mod B. All right, so let me kind of explain how this works. All right, so whoops, how do I go back? Okay, so this is an important fact, is that you actually have some control over this induced module like this. It turns out that when you take like the coordinate algebra, it has a filtration by H0 mu tensor H0 mu dual. But when you take the induction from the from the finite group up to the algebraic group, you have to twist by the Frobenius on the second factor. So it has a filtration, but it's kind of a weird filtration where you have to twist on the last factor. And this actually uses the Lang map. Okay. And then similarly, you can just apply this for n, and the only thing you leave off is the trivial factor over here. Okay. So when you do this and you set m to be equal to L lambda, it turns out that you can use the fact that GR is a normal subgroup inside of G, and you can actually use the Linden-Hochschild spectral sequence, and then you can actually relate this to the geometry of the flag variety via another spectral sequence. And when n is equal to 1 or 2, and like lambda is less than a fundamental weight, all this analysis reduces down to is the Frobenius kernel cohomology, and then you could use work of Henning-Anderson on the G-cycle of the first sheaf cohomology. So there's a lot of technical details here, but I just want to sort of say that this is what you have to do in order to analyze the third column of the long exact sequence. All right. So a nice byproduct of this was an extended calculation of the one cohomology. So we can actually now calculate, and we calculated it in the Vigor algebra group in 2011, was we looked at the weights which were less than a fundamental dominant weight. We assume that Q is bigger than 3, and then we have all these little restrictions over here. But when we do this, we can actually say that the one cohomology is actually equal to 0, except in the case of the following. So the bullet points are just the cases over here where the one cohomology is actually equal to the trivial module. So this uses the technique that I just mentioned beforehand, right? And it extends, Cline-Parshall and Scott's first work. I should ask, are there any questions up until this point?
Is anything, what is known if lambda is not less than a fundamental weight? Because there's actually a relatively small number of weights which are less than fundamental weights.
Well, there are actually quite a few. I mean, if you look at E7, you look at the Hasse diagram, Len-Chaskowski can sort of attest to this. There are lots of weights underneath, like the triality omega-4, for example.
I see.
Yeah. Not so, I mean, of course, not so much for the classical groups, but for the exceptional groups, there are quite a few.
Okay. Is anything known about larger lambdas?
Actually, no. So it's a good question. I mean, it would be really nice to extend this out further. But you can kind of use this machinery as long as you can compute. So the more computing power you have, the more chance you have of being able to actually compute the finite group cohomology. I mean, of course, finite group cohomology is very difficult in general. There's just sort of no geometry around, but we've actually inserted some geometry by using this induction functor.
Okay, thank you.
Does that good? Other questions?
That's good. Thank you.
Okay, so now we are able to actually prove rational and generic cohomology. So we actually gave a different proof of rational and generic cohomology the statement is still the same, but the difference is that we have better bounds. So using the long exact sequence that I mentioned before, we're able to actually show when the right-hand column is actually equal to 0, as long as you have certain bounds that occur. And once you show the right-hand column is 0, the restriction maps an isomorphism, and then you actually can make these identifications in this theorem over here. So, there are a lot of technical details, but this kind of gives you the bounds that you need to actually say that the restriction maps an isomorphism. The nice thing is that these bounds are uniform. The bounds that Cline, Parshall, and Scott first came up with depended on the root system. So these bounds don't depend on the root system. They're sort of generic for all root systems. And I'll just mention some other techniques that kind of came out of this, or other results that came out of this. So we could actually compute self-extensions. So we show self-extensions are 0 for finite groups of Lie type, as long as P is bigger than 3H minus 1, and you're not in type C. And then Eric Friedlander asked a question about the first non-trivial cohomology class for a finite group of Lie type. And our techniques actually allow us to actually say when or how these cohomology classes occur. Okay, so this is additional applications of what I mentioned before. So all this was sort of spurned by, earlier work of Cline, Parshall, and Scott. All right, the last topic I want to touch upon is the topic of highest weight categories. So highest weight categories were formulated in 1988 in a very important paper that Cline, Parshall, and Scott wrote that appeared in Krella. I would say it's one of their most influential works in the past 30 years. I think this was mentioned in Jack's thesis defense. So two important cases of highest weight categories are, of course, the BGG category O and the category rational G modules. So as many of you know, in these categories, there are standard modules and there are co-standard modules. So in category O, there are Verma modules and dual Verma modules. In the rational category, there are induced modules and there are also Weyl modules too, right? Now, the important thing is that the injective or projective objects, you have filtrations which satisfy orderings on the weights. And this sort of allows you to form this highest weight category setting once you actually have this. Now, when I checked last month, I'm sure that this number has gone up. The highest weight category paper in 1988 has been cited 415 times. This is according to the Math Review's citations. It's probably much higher now. And so with their highest weight category setup, what they did was they adorned it by putting on the additional casualistic theories. So they're looking at highest weight categories, which actually satisfied various X vanishing results. And so they're able to actually kind of simulate causalist theory on highest weight categories. And their model, of course, was the BGG category O. So what I'd like to do next is I'd like to show you how this can be applied. Now, as far as I know, CPS never thought about superalgebras. So this is GLMN. This is the general linear least superalgebra. All right, so I think many of you have seen this before. So the G0 component is reductive. It's just GLM cross GLN. Now, a long time ago, John Alprin defined the notion of complexity. So you take a module in the category, you take its minimal projective resolution, and you basically look at how fast it grows. And you hope it grows in sort of a polynomial way. So for finite groups, the answer is yes. For finite group schemes, the answer is yes. For restricted Lie algebras, the answer is yes. So, that sort of led on to the theory of support varieties. But this was kind of the first idea. It sort of predated support varieties. So you're just looking at rates of growth of projective resolutions. Okay. Now, a while back, Brian, John, and I actually computed the complexity. We didn't do this using geometric means. We just did it purely algebraically. So we were able to compute the complexity for all simple modules, finite dimensional simple modules for GLMN. So there's a notion of atypicality for a simple module via the invariant bilinear form. And so you can say that the complexity of the simple module is equal to this number over here, m plus n times s minus s squared plus s, where s is the atypicality. So once you're given the atypicality, you can compute the complexity completely. So how did we do this? Well, I'm not going to go over the entire calculation, but what was necessary was to use Cline-Parshall and Scott's work. All right, so let me just kind of give you a sketch and show you where it comes into play. So by using a specific bound on the dimension of projectives, we're actually able to bound the x between an irreducible and a direct sum of irreducibles. Okay, and this bound involves the atypicality. All right, now, whenever you're in the finite dimensional case, you can always use this categorical equivalence sort of proved by Gruson and Serganova. And you can reduce any block down to the principal block for smaller GLMN. Okay, so it's enough to just look at the module when I take the L lambda here to be the trivial module, and then look at a principal block for some smaller GLMN. So let's look at this calculation. So the first thing is the category script F, which is the category of finite dimensional modules for GLMN, which are semi-simple over G0. This turns out to be a highest weight category. And it has an abstract causalist theory in CPS's terminology. And this was actually proved by John Brendan. And whenever you have a causalist theory like this, you have an inner product formula via x between the standards and the co-standards with the irreducibles. So the K sigma here is a Katz module. This is like taking the dual Katz module, and you can actually form this kind of inner product formula here to calculate the x between two irreducible representations, right? And then we're able to bound this part here. This is given by a causalist polynomial. And then you can actually look at this computation over here. And this computation just involves looking at composition factors in the symmetric algebra on the odd part dual. And by an old result of Schmidt, this is multiplicity free. And then you can actually bound the dimension by the number of partitions of I with at most S parts, which is given by some polynomial function in the degree to the S. Okay, so this allows you to actually get the computation for the upper bound by using this inner product formula, which Cline-Parshall and Scott proved. Okay, whenever you have an abstract cauchy-holistic theorem. All right, so the CPS work was sort of essential in our calculation. All right, so I have a three-part epilogue. So into my notes. So as many of you know, two of the members of CPS are no longer with us. So originally the special session at Georgia Tech was to be held 2 years earlier. And Brian and Leonard were supposed to give the last 2 talks of that special session. That was supposed to be held in Charlottesville in March of 2020. So at this time, I'd like to actually acknowledge the members of CPS. So the first member I'd like to acknowledge is Edward Cline. Ed was a very good athlete. And this is from his obituary. So Ed played college football as well as rugby and soccer. He loved mathematics, but greatly admired physics lectures taught by Richard Feynman. And for Brian Parshall, who passed away last year, this is from my tribute on the UGA Algebra Group Facebook page. I was fortunate to have had the opportunity to work with Brian and learn from a true master in the area of representations of algebraic groups. I actually wrote 6 papers with Brian, and one of my favorite collaborations, which took quite a while to actually produce, was with Dave Vela, and we proved the Janssen conjecture on support varieties for Weyl modules. Okay, so now epilogue part 2, because Leonard is still with us. So Leonard Scott is still actively doing research as a McConnell Bernard Professor Emeritus at the University of Virginia. And we sort of thank Leonard for his fundamental contributions to the fields of finite and algebraic group representations, and it's for his outstanding work with CPS. We are honored to have Leonard attend our special session at Georgia Tech last month. Please join me in giving Leonard a Zoom thumbs up. I'll let you guys put the thumbs up, very good, for his many contributions to our field and his outstanding work. Thank you, all right. So last part of the epilogue. All right, now, as with any popular TV shows, there are always crossovers and spin-offs. All right, so do people know what a crossover is? It's when you take 2 shows and you kind of merge them together. Yeah, okay. Well, that actually happened. So with Brian, Leonard, and Dave Stewart, we wrote a paper with them that appeared in 2015. Leonard calls this the merging of 2-3 author collaborations. So this is hence our crossover episode. Okay. And then there have been spin-offs of CPS, and you actually heard part of this. So Jay Du gave a talk on Du, Parshall, and Scott at the AMS meeting, and also in our UGA algebra seminar recently. So they've written several papers together, sort of culminating in this large paper and exact category approach to Hecke endomorphism algebras. All right, so I'd like to conclude with a picture. This is a picture of one of CPS's favorite locations to go to. They would oftentimes take reunion trips with their wives. And this was one of them. And this is in White Sands, New Mexico in 1993, which celebrates their 20th year of collaboration. Okay, thank you very much.
Any questions for Dan?
I mean, you're free to ask questions about CPS.
How did the collaboration start?
So I believe they started, it could have been at, I think it was maybe at the Institute. So Ed was a finite group theorist. So I think Leonard knew Ed fairly well. And Leonard was sort of moving into algebraic groups at the time. And so they sort of decided to form this collaboration, but they didn't form it in finite group representations. They wanted to do something sort of new and different at the time. And in the early 1970s, algebraic groups was definitely sort of the new kind of hot thing to do.
And then how did Brian join?
So Brian and Leonard, were at UVA together.
Oh, I see. They were at UVA.
Yeah. And so Ed was at Clark for a very long time, Clark University in Massachusetts. And then he moved to the University of Oklahoma later on. And, ironically enough, John Kujawa actually is sort of the one who replaced Ed on faculty there. So after Ed retired.
Other questions for Dan? Okay, so if not, let's thank Dan again. Okay, I'm going to stop the recording here.